intermediate state when scattering from K to K prime, the spin of the electron may exchange with the impurity. And by this model, the final, we can find that the resistivity contribution to spin scattering behave like log T. Provided it is the diverge when temperature equal to 0, but when temperature equal to 0, the problem is so complicated, so we will not discuss about the temperature 0. But it's well explanation of resistor minima. So I will introduce a theoretical derivation. So the first is the electron Hamiltonian, which is perturbed, is like this term. It is the A is the creation operator, and this A dagger is a creation operator, and A is the annihilation operator. But we need to introduce the perturbed Hamiltonian, which is describe the electron scatter by the magnetic impurity. And then the first term is denote that this BS is this BS is a spin of the impurity, and because the SZ will add on the spin impurity state, will not changes the spin of the impurity, so the electron spin will not change. And then the second term and third term, since the spin impurity of the impurity will change. For example, this is minus, so the spin impurity will from up to down, and then the electron spin will get a unit by from down to up. And then so does this. And J is a parameter we can find from the experimental, and N is total atom in the crystal. So we are now, because this is a scattering process of the conducting electron in metal, so we want to find the resistivity of this process. So we need to first write down the scattering rate or the transition rate, because the duration we need. So if the initial state is A and final state is B, and the transition rate we can write as this form, and this is the A to B is this first term is the first order, and this term is second order, and the second order tell us about the spin exchange process, and consider and we also know the conservation of the energy conservation by this delta function. So and then we need to consider several scattering process, since we need to know how the electron scatter by the impurity, and initial electron with the wave vector k, and then maybe the spin is positive or negative sign, and final is to k prime, and spin can also be plus or minus. So first we consider the k plus to k prime plus. The electron with k plus is first scattered to an occupied state q prime, and then to the k prime plus. It looks like this. This is initial is k, and it is this q prime state is so-called intermediate state. It is q prime, and final to k prime. But another electron is unchanged. And then the second process, that is the occupied electron, which we shall denote by q prime, Q plus and scatter to K prime. And final is still K prime, but the occupied state Q is empty now, so the K can scatter into, the K can come into fill up the state Q plus. And so the occupied state means that the state on below the Fermi surface. And the sign of the spin may change in intermediate state. So the spin may exchange through this process. So if the K plus initial electron spin is K plus, and then to the Q prime minus, the impurity spin will increase by a unity, and then final state recover to Mn. And one of the occupied electron denoted by Q minus is scattered to K prime. Mn is also decreased by a unity and final recover to Mn. It says that the spin, we are consider the spin of electron and change from the initial state to final state. So the second order term we may write to this term, but we consider the Fermi distribution since that we need to prevent the scatter into the occupied state. It means that if this is the if an occupied state, yeah. And the expression of the second order term we can written by calculate the matrix element of the Hamiltonian, and it will be this form. But now we need to apply the energy conservation because we have this delta function in the origin. So the first term and second term can become such like this term. And then we are now, you combine the first term and second term and apply the energy conservation. This seems not include the Pauli exclusion there. So we can treat the problem of the potential scattering of the conduction electron in metal as the one electron approximation, since there's no Fermi statistic there. But we combine the third and fourth term, it written as this term, but it also involves the Fermi distribution. And the reason is that the first process we first increase the Z component of a localized spin and decrease it. And whereas the fourth, we decrease the Z component spin projection Mn and then increase it. And these two steps will not give the same answer. And it seems that the operation of the S plus and then S minus, or S minus and then S plus is not the equal commute. It's not the same because it's not commute. So therefore, we cannot cancel the term involve the Fermi and then finally involve the Fermi distribution, and so the system still exists the internal degrees of freedom spin. And then we want to calculate the second order term. So this is involved the Mn squared. It can represent by this, and this C is the concentration of impurity atoms. And then we also define this function, and this function is we can find at this term. We need to calculate it. So finally, we can get a transition probability of K scattering to K prime state. And then it is first is the K plus to K prime plus. It looks like this if we write down the total transition rate. And then there's also if the spin of the electron from initial to final is not the same, if from plus to minus, so the impurity spin will increase 1. It looks like this term, and this term is from K minus to K plus, so the Z component projection of the impurity spin will minus 1, and they involve the G of epsilon K function, and this J parameter. So we can combine all of the transition rate. It is looks like this. And then this G function we need to derive from this dimension. So we need to take a same quasi
5 minutes left.
Continuous limit. It will looks like this. It's log behavior, but and K naught is the Fermi momentum when t equal to 0, but this is diverge when t equal to 0, but we will not discuss about that. And since we want to derive the conductivity, we need to apply the current, and it causes the electric field. Since this is non-equilibrium process, we need to consider at time t the distribution function, and when equilibrium, it reduces to a Fermi distribution. And if after several times the electron still conserve, the distribution function can write to this conservation condition. It looks like this picture. And we still consider a scattering process below we need to modify. Because the scattering process, we need to add this time derivative, and then we by Taylor expansion, and we can get the final equations looks like this. And in this case, we can write to the scattering rate. This term related to scattering, we can write to this form and consider the transition probability, transition rate, or scattering rate. It is the concept from the Boltzmann transport equation. So the detail I will not discuss about that. Since this equation is very difficult to solve, assume the system can. So we assume the system can return to the equilibrium state. So it will have a time scale which is called relaxation time. So this equation may looks like more simplified. So we just consider our process of the scattering. We can we finally can get looks like this relaxation time, and we can know the relaxation time from it looks like this term. And then I directly give the conductivity of the system. It looks like this. And then we just inverse the conductivity, we can get the resistivity due to the electron spin scattering process. It looks like this term. And then we need to solve this term, so we neglect the term when we calculate this is integration, and we neglect this term, and then it will look like after several complicated integration, we will know the log behavior like temperature behavior. So this contribution of resistivity has a log function. And then as I said above, the divergence at t equal to 0 will not occur, but it is a complex CAD problem. So I will not tell about that, but we can replace the 0 temperature or the very low temperature by a T0. It is so-called a Kondo temperature, and we have a resistor minima. We can derive the resistor minima from this total resistivity contribution from the temperature power phi temperature term is the lattice vibration, and another term is contributed by the scattering by the impurity. And then just take a derivative to find a minima. We can know it's related to a concentration, and then we can take a log, and then we can from take a natural log, we can get this term.
Okay, 所以20分钟到了。Okay, so 20 minutes is up. So I think I need to stop you here. Let's thank Renren's presentation, and maybe you can go to the final slides for the summary. And we are going to enter the question section. So are there any questions from the audience? Okay, so maybe let me ask a simple one. So when you are constructing the model, there's a SD exchange, like SD interaction. So what is the microscopic origin of the SD exchange, and why there's a 1/n factor in this Hamiltonian?
Microscopic what?
Mechanism. Like what is the microscopic origin, right? You write down this term, it must mean something, right? Like why?
I think it is the electron goes with the momentum k, and then if face a magnetic impurity, and then it will scatter by the magnetic impurity, and the momentum will from the k to k prime. And then under this process, it may exchange the spin momentum. So I think the Hamiltonian describe the exchange of a spin momentum through this process. And then the n, I think it is scalar system.
Okay, so because if n is sitting right there, it means that when system size is larger, then this interaction become weaker, right? But the microscopic process where electron hit the spin and flip it, that energy scale should not depend on the system size, right? Like why there's a 1/n? Is it physical or it is just a theoretical tool?
In fact, the electron scattering will not depend on the lattice size.
我用中文讲好了，就是你的电子撞到一个大自旋的时候，它可能会有一些能量交换嘛。可是这个能量交换为什么要跟你的系统大小有关呢？因为这看起来这个微观的物理和你系统多大没有什么关系啊。所以这个 n 是物理上 存在的 n 呢，还是说它是一个理论上的工具去帮助我们做计算？
I think maybe it is a theoretical tool for us.
Okay. Okay, good. So, are there any other questions from the audience?
你可以，so I should use this English, okay?
You can use English or Mandarin.
Chinese.
Depends.
OK，
Yeah.
那我用重问，就大概问一下好了。所以，我可能有点不太专心，有点搞不太懂。就是流程的话，大概有点像是说，我先算它的 transition rate， 然后再来就是就是带到 Boltzmann equation 里面，然后去求 conductivity。就是你在求 resistivity 的时候，大概的想法是这样吗？
对，我的想法就是说，你先算一个，I can use Chinese to respond the problem.
If you feel you want to. Yeah.
I think it can more clearly since I'm very nervous before.
Okay, please.
你再说一次你的问题好了，刚刚没有提。
OK， 就流程的话，有点像是说，我现在Hamiltonian写下来，然后我们去算它的 transition rate， 就是你说 momentum， 就是电子的那个 transition rate， 然后再来就是带到后面 Boltzmann equation 这样嘛，就是流程，然后就是解。
因为我们在算波兹曼 equation 的时候，我们会需要你的 transition rate， 所以我们一定要先算 transition rate， 然后带到波兹曼 equation， 因为波兹曼 equation 还会给出说什么像 current 这样的项，就是它会给出这样的公式，然后我们只要把电场等于 sigma， 电场跟 current 的关系就是差一个电导率嘛，然后我只要把 J 除掉那个 E， 就可以得到答案，得到我们的电导率。但是我刚刚忘记讲说，我刚刚忘记讲一件事，就是我已经把所有的电场方向都只有在 x 方向，这样你就不用考虑它有向量的问题。
OK， 谢谢。
好。So are there any other questions? Okay, if not, let's thank Dunren's presentation and our next speaker. I think it's